Our group, Jolene, Miguel, Sienna, Genji, and me, are going to be presenting on L'Hopital's rule proof. Uh, okay, so here are the table of contents. First, we'll go over the background, then the proof, the importance, references, and then the task assignments. Okay, so L'Hopital's rule was first discovered and proved by the Swiss mathematician Johann Bernoulli in the late 17th century. However, the rule is named after L'Hopital, a French mathematician who published it in his 1696 book, Analyse des Infiniment Petits. Okay, so there are multiple proofs that exist for this theorem, and the method we chose is the derivative method. And the reason why we chose this is because it showcases a simple and compact proof that can be done with algebraic manipulation. This is also a proof that blends very well with calculus and can be used as a way to show the concept in the calculus class without the need of a direct graphical method to prove it.
Hello, my name is Genji and I will be taking over the proof section. So in order to find the limit of a function where it's an indeterminate form of 0 over 0, let's first determine some basis that we need to clarify. So first of all, for a indeterminate form, we have 0 over 0. So that means that the limit x approaching a of f of x and limit approaching a of g of x should be 0. Therefore, this limit here goes to 0 over 0. And then we need to say that f prime and g prime are continuous because we need to make sure that the limit works, and that since L'Hopital's rule can be reapplied, we need to make sure that f prime and g prime are continuous. So if needed, we can reapply L'Hopital's rule on f prime and g prime. And we need to make sure that after we apply L'Hopital's rule, that the g prime of a isn't equal to 0, or else it will be an undefined function. And so now we need to note that since we're using the definition of a derivative, we need to note that the f prime of a, which is the derivative, is equal to the limit of x approaching a of f of x minus f of a over x minus a. Okay, so now we have a limit x approaching a of f and g. So since we said that limit x approaching a of f and g are equal to 0, that means that when we take the limit going to f of a and g of a, both of them should approach 0. And so we have our original limit, then we subtract f of a and g of a because we're just technically subtracting 0, so nothing is changed about the actual limit itself. Then we will continue transforming this function by dividing it by x over a. And since we are dividing by x minus a on the numerator and denominator, so we're still not really changing the function, it's the same function. And now we could apply the limit to the numerator and denominator. And now if you see, after we put the limit on the numerator and denominator, these two are now the definitions of derivative. So we could take a limit, and that will result in f prime of a over g prime of a, which is equivalent to limit of x approaching a of f prime and g prime, since this limit approaches f prime of a and g prime of a. So, and we need to make sure that g prime of a doesn't equal 0, because that would result in an undefined function. Unless it's 0 over 0, then since we said that f and g prime are continuous, you could reapply L'Hopital's rule. Then, therefore, the limit x approaching a of f and g is equivalent to limit x approaching a of f prime over g prime. And I will hand it back to Nathan.
Alright, so why this proof is relevant is that it is often used in calculus when a limit has an indeterminate form, and it makes indeterminate forms easier and faster to calculate. This can potentially help to decrease computation time and make evaluating complex limits easier. Because of this, it is one of the methods that are commonly taught in the basic calculus class. Alright, so some controversies around this proof is that some educators argue that students often overuse L'Hopital's rule, applying it without fully understanding that the underlying principles of limits and derivatives. And this reliance can often overshadow the development of fundamental problem-solving skills. Alright, thank you. We love proof. Here are the references, and here are the task assignments.